Welcome back, class. So in the second session of the simulation of distillation column using shortcut method, we'll be focusing on the shortcut model. So the shortcut model will be introduced to you with the example. As shown in the model Padlet from Expen Plus, there are different types of models that are available for you to simulate the distillation column depending on the requirement of the user. So as for our case, under PSCAD subject, we will be focusing only on heavily focusing on one of the shortcut method, which is the STWU, even though there are two available in Expen Plus, and also the rigorous method, RegFrag. But in the future, if there is a need for you to use the other model, you can use it with the guidance from the user guide. So it is not difficult if you have known the basic. So for shortcut method, we are having the first method here, the STWU. The STWU is actually an approach that uses Wynne-Underwood-Gilliland shortcut design calculation. So as you learn in unit operation, Wynne method is used to estimate the minimum number of stages. Underwood method is used to estimate the minimum reflux ratio, while the Gilliland method is used to relate the actual number of stages with the reflux ratio. This model is also designed for a single feed and two product distillation column, and it can be used to simulate a distillation column for a mixture that obey to the following assumption. First is we should assume that the relative volatilities are constant and the molar overflows are also constant, despite the different composition in different tray in the column. More often, when we are given a task about a conceptual design of distillation column, then most of the questions that will pop up in your mind would be how many number of stages is required, and also what should be the reflux ratio that we set in order to get the desired separation. So you could use the STWU model in this case to get a quick idea about the process, and with the shortcut model you can also estimate the process parameters for you to put as the input for your more detailed simulation using rigorous method later on. For example, later on if we shift to RegFrag, then you need the process parameters from the shortcut method for you to proceed. So in order to use the STWU, we have to first specify the product recovery. As shown in your right hand side, there is a process flow. So you have to first specify the the product recovery for both light key and heavy key. Then the model will first estimate the minimum number of stages and also minimum reflux ratio. Then the model will calculate either the required reflux ratio or the required number of stages based on the input that we key in. During the calculation, Expen will actually estimate also the optimum feed stage location and also the reboiler and condenser duties. And finally, when the calculation are completed, you can also produce a table of number of stages with the corresponding reflux ratio. You can plot this using Expen Plus, or you can transfer the data to Microsoft Excel for the plot. Another shortcut method that is available under Expen Plus is the DISTL, and similar to the STWU, DISTL is also designed for a single feed and two product distillation process. And when we use the ISTL, we are actually also assuming the molar overflow and also the relative volatilities are constant. The only difference over here is when we put in the information, more information is actually required under the DISTL. Other than number of stages, we have to put in the reflux ratio and also the distillate to feed ratio. And finally, with the input that we key in, DISTL will actually calculate the product composition based on the administered approach. So comparing these two, the SCW is actually preferred in this case because with this input information, we are able to produce the required output for us to proceed to the rigorous method later on. Okay. Actually, these two models are similar. It's just the approach to calculate the product composition is a little bit different. Okay. And that is why in the subsequent example, we'll be focusing on the STWU. Right? So in example 1, there's a case here. We have the vapor stream containing ethylene and also ethane with the following specification. So in the feed, we are having 68.58% of ethylene and a balance of ethane. And the feed flow rate is 7.3 million pounds per day. And the pressure is 350 psig. So as mentioned over here, the product recovery for ethylene is 99.9%. So this is referring to the distillate. And the recovery of ethane is 99% in the bottom. So ethylene obviously is the light key and ethane is a heavy key. You may ask me how to determine that. You can just check the boiling point of these two components from Google. Then you will know which one is light key and which one is heavy key. Of course, you can also use a software to determine the boiling point of the component. Later on, I will show you how to do that. So the whole column here operates at 300 psi, including the reboiler and also the total condenser. You have to use Bain-Robinson as a property method and provide the reasonable gas for either number of theoretical stages or reflux ratio. Then you plot the number of stages versus reflux ratio. Then you plot with the input that you put in, then you plot the number of stages multiplied by reflux ratio versus number of stages to determine the optimum number of stages. Okay. You look at here, we have to plot number of stages multiplied by reflux ratio versus number of stages. So let's go through the steps to identify the light key and also heavy key. So for you to know the details, you can actually refer to the monograph. Okay. In chapter 3, there's a file called this003. So the details of example 4.1 is given in that file. Okay. So in order to identify the light key and heavy key, you have to first create a blank simulation. Then you'll be guided to this page for you to put in the component that are involved in the process. So in our process over here, we are having ethylene and ethane. So you just list it down. So as I mentioned to you, the best practice is you have to put in the component in the third column. Then you set the ID later on your own. Okay. So once you have all the components in the list, then you click the review button. Then there's a properties table shown up. Refer to TB, denoting boiling point. Okay. So the boiling point for ethylene is lower than the boiling point of ethane. Therefore, ethylene is the light key and ethane is the heavy key. So once you have the list of components, then you can you can move to properties tab for you to select the property model. Of course, if you don't know which tab to go, okay, you can click the next button over here. There's the next button. Then you'll be guided to the properties tab. Okay. So this is the properties page that for you to select the thermodynamic model. So as mentioned in the question, you have to select Bing Robinson. Okay. Let's select Bing Robinson. So once you have selected the thermodynamic model, then you can run the I cannot say simulation. You have to run the process in order to generate the properties for all the components involved in the process until you get the status of results available, okay, under the properties tab. So once you have done this, okay, under the properties tab, it is done with results available. Then you can shift to the next tab, the simulation tab over here. It is a simulation tab. So under simulation tab, you are given a blank page for you to construct the flow sheet. So you have to first select the DSTWU model and connect the unit operation with the stream and label it accordingly. So this is a step. So once you have done that, so the next step is you have to put in the feed information. So as I mentioned to you, if you don't know which page to go next, then you can actually click the next button over here. Then you'll be guided to a page for you to put in the feed information. So in this case, temperature is not given, but pressure is given as 350 psig. That is a feed pressure. Okay. But we know that it is mentioning in the question, it is a the feed is actually in vapor phase. So we can, rather than choosing temperature, we can choose vapor fraction. And the vapor fraction is 1 because it is in vapor phase totally, right? So the mass flow rate is given as 7.3 million pounds per day. You have to change it to mass basis. And the composition is actually in mass fraction. So just put in the fraction for the respective component accordingly. Okay. And one more point over here is the unit that we should use. Okay. I have actually changed it to English unit because based on the question given, yes, we have to choose English unit. It depends on the question. Sometimes you may need a SI unit. So the next page, if you proceed to the next step, is a page for you to put in your column information. Okay. Again, you can just click the next button for you to go to the next page on column information. So what you need to guess here is either the number of stages and also or reflux ratio. So what I have put is the number of stages, 30, and the light key recovery, okay, the recovery section here, the light key recovery is for ethylene is 99.9%, so you have to put in fraction, the recovery. Okay. While for ethane is mentioning that 99% at the bottom. Okay. So if 99% at the bottom, meaning 1% is in the distillate. Okay. So this section for heavy key here is also referring to the recovery of heavy key in the distillate. That's why it becomes 1%. You can refer to the statement over here. Okay. There's a statement saying that recovery of heavy key component in distillate. Okay. So bear this in mind. So after that, we have to put in the pressure for the condenser and reboiler and select total condenser as the condenser, the type of condenser in our column. So once you have put in the feed information and also column information, then you can run the simulation. You can run the simulation. Okay. So if you don't know what to do next, you can also click the next button. Then you'll be guided to a page for you to run the simulation. So this is the stream result generated after you run the simulation with the results available status. From here, you can easily check the purity of your top and bottom product. Not a problem. The mole fraction and also the mass fraction is also given. And in order to calculate the recovery of heavy key and light key, you can also easily calculate the recovery of the product based on the flow rate of the feed, top product, and also the bottom product, as I explained to you earlier. The equation that you need to use to calculate product recovery and product purity. So this is another page for the results. Okay, so this is a result page. So from here, you are given the estimated parameters of like minimum reflux ratio, actual reflux ratio, the number of actual stages, the feed stage, and also the distillate to feed fraction. So these are very important for you to proceed further in the rigorous method later on. So in order to generate, because just now there is a request in the question saying that we have to generate the number of stages and also the corresponding reflux ratio table and also the plot. So what you need to do is you have to go to input under the column T101. So you have the input. So under the calculation option, you have to first check here the generate table of reflux ratio versus number of theoretical stages. So with this, you have to set what is the initial number of stages and also the final number of stages. So the initial number of stages is the what do you call it? The minimum number of stages required as generated in the results just now, and the final number of stages is actually the actual number of stages as shown in the result just now. So the increment size of number of stages, I will always set 1 because this is the number of stages. So once you have this, then you can proceed to run the simulation, and this is a table generated. So you have a number of stages and also the reflux ratio. So you can transfer this data to the Microsoft Excel to plot the graph accordingly. Okay, so this is a graph plotted. What is important here, you have to get the minimum point in order to get the optimum number of stages. So the optimum number of stages here is 59. It is actually a number compromising the reflux ratio and also the number of stages, because as you know, if we increase the reflux ratio, we will increase the operating cost, but reduce the number of stages. But we increase the number of stages, we can actually reduce the reflux ratio, but we are going to increase the capital cost. Okay, in short, it is actually compromising the operating cost and also the capital cost. Okay. So that's all for example 4.1. So we'll come back later on for example 4.2. Thank you very much.